here. Okay, so it's recording now, and I will present you. So I mean, we're only four, but I present you Jacopo Gianfrani from University of Naples, and he's going to talk about natural convection in porous media in local thermal non-equilibrium. And I leave you the floor, Jacopo.
Thank you, Lorenzo. Thank you. I would like really thank you, the organizers, because of this opportunity to be here to talk about my work. So the title of my presentation is Natural Convection in Porous Media and Local Thermal Non-Equilibrium. So as you can imagine, I will focus on the phenomenon of physical thermal convection in porous media, and we will see how to model fluid motion in porous media, and I'll show you some results that I obtained so far during my PhD. So the idea, I would like to start by describing the mechanics of fluid flow through a porous medium. So I will introduce the model, which is the famous Darcy model, and I will explain the physical phenomenon of thermal convection. Then I will move on with the energy balance and the assumption of local thermal non-equilibrium. So we'll see how heat spreads in such a physical situation. And in the second half of my talk, I will focus on an optimal stability result in a particular case. And in the last section, the effect of Cattaneu's law in solid on convection will be shown. So a porous medium is a material composed by a rigid solid matrix with interconnected empty spaces called pores through which a fluid can flow. And as you can see in this picture, there is an example of porous media, and the strongly irregular distribution and the irregular dimension of pores is clear. And so if we wanted to study the motion of the single particle of the fluid, we would have a huge number of equations and a huge number of boundary conditions. So that's why the fluid together with the solid are defined as a continuum whose properties are defined as appropriate means over a volume, which is called representative elementary volume. And this volume is such that its dimensions are considerably smaller than the total volume of the medium and sufficiently larger than the pores dimension. So related to a porous medium, we find porosity, which is the ratio between the volume occupied by the empty space and the total volume of the medium. And this number is, of course, greater than 1, but greater than 0 and lower than 1. And it is useful to define a new velocity of the fluid in presence of a porous medium, the so-called seepage velocity. Here in this equation, you can see that this new velocity will be lower than capital V, which is the velocity in absence of a porous medium. And this is, of course, easy to understand because the presence of the solid matrix represents an obstacle to the fluid motion. So now if we, I would like to explain the phenomenon of thermal convection. So let me consider a horizontal porous layer saturated by an incompressible fluid and heated from below. So the phenomenon of thermal convection, as you probably know, is a physical mechanism for the heat propagation, which involves a by means, of motion of particles of matter. We call natural convection when the motion of the fluid is induced by a difference in the fluid density due to the presence of the gradient of temperature. So as you can see, in this case, we find a less dense region at the bottom of the layer and a denser region on the top of the layer. So particles of the fluid which are closer to the lower plane, they tend to get wider and lighter, and so they tend to raise up because of the buoyant force of Archimedes. But this force is initially balanced by the viscosity of the fluid and the gravitational force. Initially the fluid keeps staying at rest, but the presence of the temperature gradient makes this situation potentially unstable. So we have that once this buoyant force of Archimedes overcomes the opposite forces, the fluid motion begins, and we will have the onset of thermal convection. So what happens? Particles from the bottom raises up, and they cool down, they get heavier, and so because of gravity, they draw. And so this periodic motion occurs, and actually this motion is repeated within the layer. Now, I would like to show you just an example of thermal convection. So as you can see, we have a horizontal layer heated from below. And what happens is this vertical motion of particles. And we have that, as you can notice, this periodic motion of particles. And in particular, we can notice that the fluid is divided in cells. And in every single cell, the fluid motion is always the same. So we can say that once once convection occurs, the fluid, fluid is divided in cells. These cells are called convective cells and are repeated periodically within the layer. And in every single cell, the fluid motion is always the same. So from a mathematical point of view, this is very important because we can analyze the fluid motion within a single cell. So what's the aim of our analysis? We have the initial solution, which is a solution with fluid at rest and it's spreading by conduction. We want to study the instability of this solution, and we look at convection as the instability of our conduction solution. Actually, from a mathematical point of view, we have that convection occurs once the dimensionless Rayleigh number here defined overcomes a critical value. So we want to determine necessary and sufficient condition for the onset of convection on this Rayleigh number. And we want to determine a critical threshold for this number beyond which thermal convection occurs.
Jacopo, can you make a quick comment on why this is periodic? Because I don't see, is there some mechanism that makes this periodic? Or is this just an assumption?
Of course. Yeah. You can see here, you can see the idea of this periodicity because you see that particles here at the bottom of the layer, because of the bottom layer is hot, they get lighter. So because of
this I understand,
yeah.
but you're saying that the cells are roughly the same, right?
Yeah. It's merely empirical. Okay. You can notice, this is a picture of a convection phenomenon from above. So this one is a convective cell from above. So you can see that actually they have this structure and they are repeated periodically within the layer. And you can notice perfectly that in every single cell, the motion is always the same. So yeah, that's it.
Thanks.
How to describe the fluid motion in presence of a porous medium? In 1856, the engineer Darcy obtained this law experimentally, and this law shows a proportionality between the gradient of pressure and the seepage velocity. Once on the porous medium an additional force acts, this law needs to be modified accordingly to as shown in the equation number 3. What about the energy balance? If we usually when we have something that we want to balance, on the right hand side of our equation, we need two terms, one for production of something, the other one for a flux across the boundary. So in this case, if C is a fluid volume. We want to balance the internal energy of this volume. So we need two terms. One is due to sources, the other one is the flux across the boundary. And now, since we are dealing with temperature, we can employ the famous Fourier's law as constitutive law for the heat flux. And by substituting this kind of constitutive equation in the previous equation, we end up with equation number 6, where actually this term is usually neglected. And actually in equation number 6, we can get rid of this term because of the incompressibility of our fluid. And now I would like, this is the energy balance equation, but I would like to remark that if we assume that if we could neglect this nonlinear term, we end up with a parabolic heat equation. And this leads to some paradox, and we will talk about it later. So now, what does it change if instead of a so-called clear fluid, we have a fluid in presence of a porous medium? We can proceed with two strategies. We can either assume the local thermal equilibrium hypothesis, for which temperature of fluid and solid are equal. And in this case, we need just one temperature equation that is here defined. Or we can employ the local thermal non-equilibrium hypothesis, for which in this case, fluid temperature and solid temperature are different, and so heat exchange between the phases are allowed. So in this case, we need two temperature equations, these ones. And since there is interaction between the phases, we need to model this interaction by introducing this term in both equations. Now, let me just underline the presence of, in the fluid temperature equation, of this nonlinear term, which describes how the fluid temperature is affected by the fluid motion. That's why it's called the convective term. And of course, when does this assumption hold instead of the local thermal equilibrium one? There are two cases. The first one is when the fluid velocity is large, because in such a case, the interaction coefficient H is large as well, or when the difference between the thermal conductivities is large as well. I mean, thermal conductivities of fluid and solid, because in this case, of course, heat spreads in a different manner depending on the phase. So now, in order to show you the optimal stability result, I need to introduce some additional hypotheses on the porous layer. So in this case, we have considered a porous layer which is rotating uniformly about the vertical axis. So from a mathematical point of view, it is more convenient to define the fluid motion in the rotating frame. So we need to introduce this change of reference, and we need to modify the Darcy's law in the rotating frame. So in this case, we have that the momentum equation is the following, number 10, where we find a new pressure, which is called reduced pressure. And in particular, we find this term, which describes the presence of the action of Coriolis acceleration on fluid motion. As you can notice, this term has only horizontal components. So you can imagine that the rotation encourage the fluid motion in the horizontal directions, while discouraging the motion in the vertical one. So since our instability is a vertical motion, we would expect that the action of rotation delays the onset of instability. Another assumption is about the anisotropy of porous layer. So anisotropy is the property of a material for which its features depends on the direction. And in this case, we are taking into account a porous medium for which permeability and thermal conductivities are anisotropic. So the model describing our problem is the following, where first equation is the Darcy's law, where we find a term due to rotation, and this term which is due to the gravitational force. And last few equations, which are the energy balance equation. And this is, of course, the Fourier's law, now slightly modified because of the presence of anisotropic thermal conductivity. So we are, as I said before, we want to study the stability of the conduction solution, which is called M0. This solution describes a situation with fluid at rest and heat spreading by conduction. And in order to study the stability, we need, of course, to introduce perturbation fields. We end up with this dimensionless model number 13, where some relevant parameters appear. We find the Rayleigh number, which is, as I said before, the main responsible for the onset of convection. And in the first equation, we find also the Taylor number, which takes into account the presence of rotation. It describes how rotation acts on the fluid motion. So since we can analyze the fluid motion in a single cell, we can reduce our analysis and linear instability analysis to a single cell. We define V as the periodicity cell, and we assume that perturbations are periodic in X and Y direction. The linear version of previous model is the following, number 15, where actually the first equation has been written retaining only the main unknowns. W is the third component of velocity, and again, we are interested in vertical motion, so that's why only the third component of velocity is relevant and appears here. For this model, we managed to prove that the linear operator related to this model is a subset of real numbers. So for this case, we have that when convection arises, it can occur only through steady motions. This is easy to understand because, of course, if the eigenvalues are real, we have that instability occurs once an eigenvalue crosses the zero value. So now, since the previous model is autonomous, we can look for solution for which the spatial dependence is separated from the temporal one. And of course, because of periodicity, we can look for this kind of solution, which are called normal mode solutions. And now I won't go through the all calculations, but if we put ourselves in the marginal state, so when the eigenvalue sigma is equal to 0, we end up with a single equation, number 19. And from this equation, we can determine the critical threshold for the Rayleigh number for the linear case. Of course, we need to solve this minimum problem. So we can, in such a way, obtain the critical threshold RL. And this analysis tells us that once the Rayleigh number overcomes RL, the critical Rayleigh number, we have instability. And let me just notice that in this expression, we find the Taylor number. And as you can see, the greater is the Taylor number, the greater is the critical threshold. So this is a confirmation of the fact that rotation delays the onset of convection. Now, to proceed with the nonlinear stability analysis, what we want to do when we perform a nonlinear stability analysis, we want to determine a sufficient condition for which the L2 norm of our unknown fields goes to 0. Since this inequality 21 is true, if we had a control on the theta norm, we automatically have a control on the U norm. So we need to just control theta and phi, which are the last unknown fields. So we start from the nonlinear model 22 with the first equation written as in the linear case. We define these three functions, where in particular E is the Lyapunov function. And we know that sufficient condition for the stability of our solution is that the time derivative of this Lyapunov function is negative. So we can write the time derivative of E, and we easily can obtain this inequality 23, where Re is solution of this variational problem. From 23, we have that if the Rayleigh number is lower than Re, then the time derivative is negative. And so this is a sufficient condition for the stability. So all we have to do now is to determine the critical threshold Re by solving this variational problem. By doing so, we obtain the equation 26, which is the same equation as in the linear case. So we obtain the coincidence between, since from equation 26 we can determine the critical threshold Re, we obtain a coincidence between the global nonlinear stability threshold and the linear instability one. So in this case, we have that when R, the Rayleigh number, is lower than Re, this is not only a sufficient condition, as I said before, but also a necessary one for the nonlinear stability. Now, what about the energy balance? So the last part of my presentation. We wondered what happened if instead of the famous Fourier's law, we employ Cattaneu's law. As you probably know, Cattaneu's law has been introduced in order to overcome the Fourier paradox. According to this paradox, we have that a disturbance in temperature in a domain is felt instantly in the whole domain. So this means that it spreads at infinite velocity. And this is quite simple to understand, because if we have this parabolic heat equation and we have a disturbation on the initial data, this disturbance is felt instantly in the whole domain. As you can see, this is the solution of this problem, and slightly modification on G is felt instantly in the whole space. So Cattaneo introduced this law, which, unlike the Fourier's law, in this law appears only this inertia term, and where tau is called thermal relaxation time, and it describes the time lag required to establish a conduction in a volume once a gradient of temperature has been imposed across that volume. So by employing the previous energy balance equation together with this Cattaneo's law, we end up with an hyperbolic heat equation, which now allows us to say that thermal waves propagates at finite velocity. So now the model we have studied is the following, where we find in the fluid temperature equation the Fourier's law is retained, the Fourier's law, while in the solid temperature equation we find Cattaneo's law. This choice, of course, is based on physical consideration, because the effect of thermal inertia has been noticed only in the rigid conductors. So again, we want to study the stability of the conduction solution of the previous model. We introduce perturbations and obtain this dimensionless system 33. We find here the Rayleigh number, and of course this parameter, which describes how the presence of thermal inertia affects the convection, the instability. So by performing now the linear instability analysis, we obtain this expression for the Rayleigh number, equation number 34. But now, unlike the previous case, we do not have that the eigenvalues are only real numbers, but they can also be complex numbers. So in this case, we have that convection can occur through either oscillatory or steady motions. So we have to determine both a critical threshold for the steady convection and a critical threshold for an oscillatory convection. The nonlinear stability analysis provides the critical threshold for the nonlinear case, Re. And in this case, we have that this threshold Re is always lower than RL, which is the minimum between the previous two thresholds. I won't show you all the expression of this function because they are really complex, but this is only the last thing I want you to notice, because what about the effect of Catania's law, the presence of Catania's law on the onset of convection? First of all, the steady convection is not affected by the presence of Catania's law, because critical threshold Rs does not depend on this parameter at tau. Actually, when this parameter is equal to 0, the conditions for the existence of oscillatory convection are not satisfied. And once this parameter is different from 0, we have that the presence of Catania's law can imply the existence of oscillatory convection. So just now to sum up what I've shown you so far, in general for stability problems, we have that linear and nonlinear results does not coincide. We have that when the Rayleigh number is greater than RL, we find instability. Before RE, we have nonlinear stability, but we don't know what happens in the between. What we managed to obtain in the first case, we had a coincidence between these two thresholds. So in this case, this region is empty, and this implies that R lower than RE is not a necessary and sufficient condition for the nonlinear stability, and in this sense, the result is optimal. Thank you.